Finster here. He's been visiting us for 2 weeks. Had a good time last week. Nice talk earlier in the week. The second talk.
That's
Type-Theoretic view of the Goodwillie calculus, right?
So last time, yeah, so my title was the Type-Theoretic view, but last time we saw essentially no Type-Theoretic. Part 2, hopefully we'll do some Type-Theoretic today. Yeah, so yeah, again, thanks to Steve also for inviting us. It's been a really nice 2 weeks. Okay, so let's sort of pick up where we last thought. So last lecture was really a bunch of motivation, but let me just recall where we ended. We sort of ended with this idea that we were interested in thinking about functors from finite pointed spaces into spaces, and we were sort of imagining these functors as kind of approximating the homotopy types of our finite spaces, for example, and calculating homotopy invariance of the results of these functors. And then we sort of found, or I sort of explained, that there turns out to be a very natural way of forcing these invariants, forcing your functors to spit out invariants that are much easier to compute. And that's in some sense what Goodwillie calculus is about. And we sort of ended by saying that there was this endofunctor Pn, one for every n, which I called the nth excessive approximation to a particular functor. And in particular, applying these Pn's to the identity spits out something very nice because it lets you approximate unstable homotopy types by successively incorporating more and more complicated information. And what I said, what I sort of sketched but didn't prove completely, is that Pn is always a left exact modality. Okay. So in this talk, I want to recast this story, just in a sense, in terms of this observation here. That I want to speak about left exact modalities and their sort of properties inside of type theory. Okay, so, but before I do that, I want to develop just a little bit. I'm going to try to do this relatively quickly. I want to develop a sort of a little bit of notation and a particular concept that are going to give us some tools that are convenient to work with. So let me, in what follows, fix 2 type families, P and Q. Let me, so I'm sort of, in this subject, a little bit schizophrenic because most of my co-authors think a lot about higher category theory and topos theory, and I like type theory quite a lot. So, so there's this sort of internal version and sort of external version. So maybe just in this first slide, I'll sort of, well, just write down the 2. Maybe this isn't a perfectly good notation. That in type theory we have this complete equivalence between families and maps. And so what I'm gonna, when I sort of speak in this schizophrenic language, I don't really distinguish between families and maps. Okay, so that means sort of for every construction I can do on maps, there's a corresponding construction in type theory. And so I need to sort of pick a side, unfortunately, but it's hard to pick a side because sometimes things. So there's a number of interesting constructions in topos theory. If I have a map, I can always look at its diagonal, right? So this would be the map. Well, as I've written it here, it would be P hat mapping to P hat over A P hat. And if P is my corresponding family, then I'm just going to write the same thing, the diagonal of P. And what is it? It's a family over now not just A, but PA across PA. Mapping to type, and it's defined by A, P0, P1, mapping to P0 equals P1. Okay? So when I write the diagonal of the family, I mean the family of all of its identity types. And that's exactly what this sort of topos theoretic construction corresponds to. There's also what I will write as the codiagonal of a family, which is A maps not to A, but to the suspension of P of A. So this is the fiberwise suspension. And this also just has a completely analogous description. So this time it would be what? Oh, I should have done this before. So I guess it's going to be A pushed out over P hat A, mapping to A. Is that right? Okay. So and it's really the universality of co-limiting in a topos that tells me that this really is fiber-wise the suspension of fiber. So there's an internal version over here. And there's also this other construction that is extremely useful in the story I'm about to tell, which is the pointwise join of two families. So I take P and Q, and now I'm going to give you a family over not A or B, but over A cross B. And this is the family that sends A and B to P of A join in the topological sense with Q of B. And you can work out that this really is the push-out product of these two maps on the sort of topos theoretic side. Okay, this is how it looks. And again, by universality of colimits. And if you do that, that actually means, because we're going to use it later, that using this presentation, remember the suspension can be thought of as the join with S naught. So that means I can write the codiagonal of the map as its box product with S naught, where S naught is the map to 1. And that also means over here the same thing. That this is also P box product with S naught.
So this sigma is not the sigma type, it's the...
That's the suspension, right? Yeah, the topological suspension. But it's also the box product of maps. So, so in what I'm going to do, we're going to see that I'm going to, at various times it's convenient to use one picture or the other. And notice also I'm going to have this convention that if I have just a type, so a trivial family, I'll just write the type as if it was a family. So here I'm writing S naught, but I really mean the type family over 1, mapping the point to S naught to be totally rigorous. Okay.
And when you do these push outs on the right,
Yeah.
You're working in an infinity category,
Right.
and if you were working in a model category, you'd have to put in a fiber replacement or
Right.
something.
Right. Exactly. Yeah. And so you see that here that the type theory just gives us kind of directly what the fiber
Builds it.
replacement would have been. Yeah. Exactly. Okay. Great. So with these conventions, let me just make a definition. There's a kind of partial order on family. So every family, so every family, as we sort of saw in Edward's talk, generates a modality, which is the modality which forces all of the types in this family to become contractible. Okay, that's called nullification at P. And so you get a modality for every type family, the nullification at P. Okay. And so this induces a relation on type families where I can say P is, well, I'm going to say less than or equal. I'm just going to write less than or equal. Well, you can complain. There's probably a better symbol for this, but let's just, there's not going to be any other ordering today. Where I say that P is less than Q if for every A and A, the Q modality applied to every fiber. Oops, let me, I was about to do non-type theory. So it's contractible. The Q nullification of the fibers of P. Okay? So this says, in other words, Q, every modality determines the collection of connected types. These are the types which become contractible when I apply the modality. And this P less than Q just says that all the types in P are Q connected. Okay? So this is going to be a convenient tool to manipulate. Yeah.
Before you go on, the modalities go by nullifying P.
Yes, right. Nullifying all of the elements of P, right. And on this side, I'll sometimes speak of the modality generated by a map. And I mean nullifying its fibers, which is slightly different than forcing it to be invertible. These two things don't coincide in general. There's this difference between localization. But I'm only speaking about modalities today. There will be no localization. Yeah, hopefully.
The difference is whether it's left exact.
Those two things coincide when the map generates a left exact modality. but in general, they're different. A nice example to work out is like you take S1 and you map it S1 by multiplication by P times, and you can localize by this map, or some variant of it, and you get P local spaces. But the fibers of this map are just P points. So if I modally localize it, I just get -1 truncation. And those two things are different. So localizing and modalities are different things. But okay, we're only talking about modalities today. We're only killing a collection of spaces as opposed to inverting a map. Yeah.
What is the?
Let's not focus on this too much because there's I have a lot to do. Okay, so here's a first sort of proposition. Well, so let me say that P. I'm gonna say P is everywhere inhabited. If for all A in A, I have -1 truncation of P. Okay, so this is just going to be, since I'm going to speak a lot about families, I'm going to say everywhere inhabited. On this side of the board, that would just say that the map P is surjective. Okay, it's a cover. This is on the right hand side. Okay, so following your equivalent. P is everywhere inhabited, and the diagonal of P is less than or equal to 2, or 2. P is less than or equal to the codiagonal. Okay, so you have this kind of a junction formula with respect to the diagonal and the codiagonal, except for here you need this extra condition of being everywhere inhabited. So why is this true? Proof. Well, sketch proof. I think all my proofs are going to be sort of sketch proofs because there's a lot of things I do. The main tool to see this is that for any type, say, I want to say A, say S, that if I take S0 equals S1, so the identity type in S, and I modally apply Q, this doesn't commute, but you can say something. What you can say is that this is, again, an identity type, and it's an identity type in S modally killed with respect to the codiagonal of Q. And then you just take the canonical inclusions. Okay, so so you have this fact that when I apply modalities to identity types, I lose, if you like, in a certain sense, one modal suspension. Okay, and by the way, we're going to talk about Lex modalities, and one characterization of Lex modalities is that I can reduce this back to Q, and this works for Q itself. Okay, so given that, let's see. So 1 implies 2. I forget which one is going to be easy. So I'm going to apply that in this case. So by the way, so it suffices when, and this is going to be a usual trick when I'm sort of working fiber-wise with these things right here. The A or the B, where I say for every type, is just a parameter, and so it's going to be convenient in the notation to ignore it. I'm always working fiber-wise, so it suffices to consider the case A equals 1, in which case P is just a type. Okay, and so now I'm sort of reduced to the case before. I'm trying to show that if P is everywhere inhabited, then the diagonal of P is less than Q. So I'm trying to show, so we're considering in this case, we have a P0 and a P1, and I'm considering its modal reflection, and I'm supposed to show that it's contractible. Well, no, I assume that it's contractible, and I'm supposed to show this relation right here. Okay, so by my formula, I'm just going to use my formula right here. P0 equals P1 in P, but modally reflected as a codiagonal Q. And so what's my assumption here? My assumption is that P is everywhere inhabited, and the diagonal of P is less than Q. That means if I apply Q to any diagonal, any path space in P, I get a point. That says that the left-hand side is contractible. Yeah, that's my assumption. The left-hand side is contractible. So the right-hand side is contractible. But the right-hand side being contractible says that that the modal reflection of P with respect to the codiagonal of Q is a proposition. Okay, but if it's everywhere inhabited, it's also an inhabited proposition, so it's contractible. So that's where I use my second hypothesis. And conversely, the converse one should be easy actually. If P is contractible for the codiagonal P, well, that means this is contractible. So this is contractible. So this is contractible, which is the other way. Okay. So so that's that. Okay. So we have this this junction. And I'm going to sort of exploit these inequalities.
Get more boards.
Oh, I do have more boards. Sorry, I forgot about that. Okay, good. That would have been smart. Next time I'll
Just
yeah.
check this order on spheres. This is reverse.
Okay, I thought a lot about, so there's been a lot of debates about the order. This one has the nice fact, consequence that, that if P and Q really are propositions, then this relation is the same as Q implies P. So I'll let you.
There's a reason to reverse it. Okay.
So
Yeah, it's another reason
There's a reason to use the other order.
oh, really? Oh, but I was thinking of this as an implication. Okay, you can always do both. So we've been debating about this all week. So I'll just use this one for today. The debate will rage. Okay, so now we wanted to talk about Lex modalities. This is sort of the goal, and so now I'm gonna. So here's a sort of theorem about that. Joined with all my co-authors, the following are one, the modality generated by my family is left exact. And two, the diagonal of P is less than P. Okay, so I think this is roughly one of the characterizations that was in paper, in Mike's and Baz's paper. They said that a modality was left exact if the path types of every connected type were themselves connected. This just says it suffices to check that for the generator itself. Okay, so it's sort of not so unexpected result. So let's again sketch proof. Right. So there's a number of you can look them up in their paper. There's a number of different characterizations of what it means to be a Lex modality. One of the sort of the nicest, is sort of from a conceptual point of view, is a Lex modality. A modality is Lex if the universe of modal types is again modal. Okay, so that's what I'm going to attempt to prove from this condition right here. And it's not so. So let me write UP for the universe of modal types. So what does it mean actually for the universe of modal types to be modal? Well, the characterization of the nullification with respect to P to be modal is to be what we call orthogonal to P. So it's to have the lifting property with respect to P. Again, let me take A equals 1. The proof, if you're interested in families, is identical. You just have an extra parameter. So what do we want? So what am I saying by that? To say that P is orthogonal to the universe says that for every such square, I'll have a unique lift like this. Unfolding that, what does that mean? Let me call this X. This says for any type family of modal types over P, there exists a type such that every fiber of P is equivalent to that type. Okay, so let me write that. That says, so enough to show for every modal family over P, there exists, and it's automatically unique, so I maybe want to do the uniqueness, a modal type Y, such that for all P and P, the value of my fibration at P is constantly, well, okay, is equivalent to Y. Okay, so that's just a rephrasing of the definition right here of what it means for the universe to be modal. Okay, so how are we going to show this? How am I going to show this? I'm going to take. It turns out that if this is true, there's a necessary answer. There's only one choice. I'm going to take Y to be exactly the space of sections. This. And so then what do we need to show? Oh. Okay. So then what we need to show, well, let's fix a P naught. And we need to show that X of P naught is equivalent to the space of sections P X of P. Okay. So how are we going to do this? Right. So here's a fact. So if S and T are modal types, then the type of equivalences between S and T is itself a modal type. Okay, so this is a standard fact. If you just write out what equivalence means, it's a series of sigmas and pi's, all of which preserve things being modal. So the type of equivalences is always modal type. Another way to say that is that P, I'm going to use this orthogonality symbol. So P is orthogonal to S is equivalent to T. Okay, but this relation, it turns out an equivalent characterization of this relation, just by playing with the notions of orthogonality, is that something on the left, Q is less than P, if every type which is orthogonal to P is also orthogonal to delta P. Okay, so that's just playing with the orthogonality relation. So that means that because equivalences are modal, and because delta P is less than P, equivalences are also orthogonal to the diagonal of P. Okay, so that's the first step. But now, so let's see. Let's look at. Let's suppose that we have two elements of P and they're equal. Then I have the map app. Let me just say. Let's suppose that I have two elements. So I have the map app, which goes from P naught to P1 to X of P naught is equivalent to X of P1. That's just by apping P. Yeah. So that lives where? That lives in the type X is equivalent to XP1, exponentiated by P1 equals P1. That's app lives here. But this relation says that if you unfold the orthogonality relation, it just says that this map, the constant map, is an equivalence. Okay. So that means if I have two elements P0 and P1, and I look at app, I can choose an element in the inverse here. Okay. So for any two elements, I'm going to call that alpha of P0 P1, and alpha of P0 P1 is always an equivalence between the two fibers. Okay. So the interesting thing you see from this construction is that I'm able to produce an equivalence between any two fibers, which is completely independent of the path. Okay. So since I have a lot to do, maybe I'll just leave it here. Okay. So if I have an equivalence between any two fibers, which is completely independent of the path, then my fibration is constant because it can't move. Okay. So for time's sake, I'm just going to leave it here and move on. This is the basic idea. If you now you'll now produce a map from here to here by using alpha, because if I have an element here and I have another P, then I can just apply alpha P0 P1 and get an element here. That'll be my section, and then the composition will tell me that that map is inverse. Okay. Okay. That's the essential idea, yeah. What's your... Ah, I did it again. So every time you see me walking like this, you just have to say, raise the floor. Okay. So, okay, so this is, oh, I just erased the theorem. Oh, that's right. P-lex. Okay, well, so a nice corollary of this fact is that every family has a Lex closure. Okay, because because P you think of as giving you the family of types that you're trying to force to be contractible. And well, it's Lex if and only if all of the diagonals of P are also forced to be contractible. But I can do that, I can force that condition to be true by just adding all of the diagonals of P. Okay, so in other words, yeah, let me just write it like this. I could give a nice recursive definition, but just let me schematically say that if I take the disjoint union, it really is the disjoint union of all the diagonals of P, from n equals 1 to infinity. This is a new family. It's indexed over something slightly more complicated, but it's some new family. But this always generates a Lex modality. And so that's nice, because that means that we can now produce Lex modalities from nowhere, from anything. Okay? So anything. And yeah, so and you might notice that there's this classical theorem that says that this theorem that says that if P is a family of propositions, then it always generates a Lex modality. And from this characterization, that's completely clear because the diagonal of propositions are contractible. So this is not an extra condition when P is a proposition. So right. And this is exactly the property, if you like, that fails for the spheres. Okay, this is why truncations are not Lex modalities, because their path spaces are extremely complicated, and the truncation modalities are just generated by a single sphere. It's missing the rest of the information to force it to be Lex. Okay. So that's good. Next observation. Okay, the next thing I think that I want to prove. So we have this well, I'm just going to state it. Okay, so the next theorem is a closure property. If I have two modalities, then the modality generated by the pointwise join is also Lex. Okay. So okay. So the Lex modalities are closed under the operation of taking pointwise joins. Okay. So let's try to prove this. Okay. So let me just recall over here. So P box Q was the type family sending A and B to P of A join Q of B. Okay. So sorry? Thank you. Yeah. Okay. So, how to see this? Again, again, this is a completely fiberwise condition. It suffices to do A equals B equals 1. There's no, yeah, the A and B will just be carried around as a parameter in, Okay, I forgot something. Okay, I need a lemma, so we'll come back to this. Okay. So I need a lemma. Where can I put my lemma? Thank you. Thank you. Okay. Yeah, okay, but that one, that's really like that. Yeah. Okay, so lemma, warm up, is that suppose that P is a Lex modality. Yeah, with generator P. I hope that notation has been. And that P is everywhere non-empty, inhabited, I guess I would say. Okay, so if I have a Lex modality and the generator is everywhere inhabited, then P box Q is Lex for any family Q. Okay, so if I have this extra condition, then okay, should I try to use that back one? Well, that's going to cover up the proof. Yeah. So this is fairly straightforward. So this is really on the way to proving that anyway. So let's see. So why is this true? So suppose. Okay. So suppose P Lex and everywhere inhabited. So because it's Lex, I have by the characterization that the diagonal of P is less than P. This was the equivalent condition to being Lex. But by this adjunction formula, whenever P is non-empty, I can trade in this diagonal and move it over the other side. So I get P is less than or equal to the codiagonal of P. Yeah. Okay. But now, for any Q, boxing with Q preserves inequalities. That's something which is easy to see by orthogonality. So I'll let that. So this implies that for any Q, that I have P box Q is less than or equal to the codiagonal of P box Q. But the codiagonal we saw was boxing with S naught. So this operation on the right-hand side is associative. So so I can re-associate like this. But now I can move the codiagonal back to the other side, and I get this. Which is what we wanted to prove. Yeah. So now we're over here. And what do we want to do? So I want to use the lemma, okay? So what I want to show is I want to use this lemma, and I want to argue that, in fact, in the proof of this theorem, it suffices to suppose that either one of P or Q is non-empty. Okay? Why is that? So claim. So this is now the proof of the lemma over here. I can write it like this. So first, let's observe the following. I can take, okay, I'm going to again take A, B equals 1. Nothing will change. So P and Q are now just single spaces, which happen to generate Lex modalities. It won't change anything. So and the box product when P and Q are just spaces turns into just the join of these two spaces. So I have this map right here. So I'm gonna consider the -1 truncation of P join Q. But -1 truncation commutes with the join. So this is this. And now it's a sort of well-known fact in people in HoTT that the join of two propositions, and this is now a proposition, is implemented by the truncation of their disjoint union. Okay, so now I have this map, and now what I'm going to do is I'm going to apply P join Q modality to this map. Okay, I've got a lot of bars. Sorry about that. I've got a lot of bars now. But now this is contractible. And this is a proposition. So I have a map from a contractible type to a proposition. So this is contractible. In other words, this type is always inhabited. Okay? So now, I want to prove this type. I'm going to use it because it's always inhabited to produce a map from this to the following type, to the statement that for all P and Q and P join Q, the modal reflection, so is contractible. The modal reflection of P equals Q. This is just a statement of what we wanted to prove, slightly diagonally. Okay, we wanted to prove that the modal reflection of P join Q, that the diagonals, the path spaces in P join Q are always contractible for this type. That's equivalent to it being Lex. But now this type is P join Q modal because because this is P join Q modal, and its contractibility, if you expand it out, will be, and pi of it will be. So I can remove this because the outside is P join Q modal. Sorry, this is now. Okay. On the other hand, this is a proposition, so I can remove this. Okay. And this just says that in order to prove this, I can assume P or Q are non-empty. But then I apply the theorem that when one of P or Q is non-empty, joining with anything gives a Lex modality. Okay. Okay. So these are the sort of two things that we now have, is that we can sort of generate Lex modalities from anywhere. We just need to complete families by their diagonals, and that they're closed to undertaking the box products of two modalities. Okay, so sort of here's the theorem. We were in the following, we were thinking about the Goodwillie tower. And the Goodwillie tower was that we were thinking about functors from finite pointing spaces to spaces. And in this topos, there's a canonical object, the universal, so we sometimes write this as S join a universal pointed object. This is a nice description of this topos. And the universal object in here is what I'll call X dot, which is the forgetful functor. Very classic topos theoretic argument. The forgetful functor from finite pointed spaces into spaces is the universal pointed connected space. Okay. So we have this object here, and that means that I can consider. Let me write. So here's my object, and let me write somehow the. I'm going to sort of imagine that my left exact modality is like generating a bunch of maps from X, and I'm just sort of write it like this. So it's kind of like the ideal, if you like, generated by X inside this topos. Okay? So there's a modality, and what I'm saying is, okay, so any object of my topos generates a modality, and I want to generate the Lex modality generated by X star. Okay, so this means it's the modality generated by X star together with all of its diagonals. Okay? I might write it. And now, so this is, so it's not hard to see. It's essentially by definition, in fact. Our Lex modalities, topos theoretically, they correspond to localizations because it's a Lex modality generates a reflection functor which preserves finite limits. Okay, so that means that if I kill X, it's easy to see that in this case, I'll just get back to spaces, if you like, because this topos is sort of, in a sense, freely generated by this object. So if I force it to be contractible, I get back to spaces right here.
Sometimes you're writing dot and sometimes you're writing star.
You're right, I am. Does anyone have a preference? Yeah. Let's think about that. Okay. But by the theorem, anytime I box two modalities together, I get a new modality. So what I can do is I can look at the nth box power of this modality. Okay. And because this one was Lex, the rest of them are Lex. And so I'm sort of writing this schematically for being the modality, and the theorem is that this is Goodwillie's Pn. So so I'm going to write this as this sort of schematically speaking. So now I know I'm not supposed to erase, but I'm going to put it right back. The picture of this. So S, in other words, we're sort of thinking this, we're using this analogy that toposes are kind of like commutative rings, which I learned from Mathieu, which is really beautiful in this case, which is that this, I can write S box X as well. It's X adjoined X, but then mod X. Okay, so that's that. And so then you get, well, okay, I'll talk about what you get up there in just a second. So then we get a whole family of towers where we don't kill X, but we kill the powers of X. And at the top here, well, I'm going to talk in just a second about what we get here, but it turns out these all factor through what I would call the infinitely connected localization. Okay, so yeah.
So if I think of this algebraic geometry setting, I have the line.
Yep.
And now I look at the neighborhoods, the infinitesimal neighborhoods, full neighborhood of 0.
That's exactly right.
But how did I pick the point, the origin point? Is that this pointing? Can I pick a different point?
Great question. It's harder. This is we've been sort of working on this question for a long time. Probably yes.
Okay.
But it's not as considered. Yeah, that's exactly right. You can think of Sx is somehow the line, the analog of the affine line of pointed spaces, and S is just the point, Type-Theoretically, and so you have this beautiful interpretation of the Goodwillie tower as the formal neighborhoods of the point in the affine line of spaces. Okay, but I mean, this is considerably more general. Oh, maybe I will come on to this sort of thing. Because this is, in some sense, the sort of universal example of this, but this works in complete generality. I mean, if I have any topos and any localization of that topos by something which is left exact, so am I using 2 bars or 1? Sometimes we use 2 bars, so I'm not sure why. By some, and I'll just write it as I to have fun. So for any, and I is the class, if you like, of connected maps for some modality, then as we've seen, we can just take powers and we get a sequence of expansion. So this is something which is invisible in a certain sense in one topos theory. Oh, so let's see why. So here's a quick calculation of why. So here's a lemma. If P, I'm going back to my sort of type theory notation, if P is a family of propositions, so that the modality is what people call tautological, then this tower is constant. So this tower does not do anything if your modality is topological. Okay, and in one topos theory, every localization is topological. So this is, in a sense, an aspect of higher category theory which is completely invisible to one topos theory.
Constant after 1 step, or it's already constant.
Period.
After 0 step.
0 step. So let's try to I'm going to switch a little bit to. Just because I know this truth in this case, to the case where I'm working with maps, and this being a family of propositions means this map is a monomorphism. Okay.
Curly?
Oh.
Yeah.
What?
You had written A in 2 different fonts. Okay, that was
I see. Okay. So what's the point? Well, so the point is that so you have always this inequality. So you have F being less than equal to itself. And one fact about these things is that you can always, the left side is closed by boxing with absolutely any map. Okay, you can put any map here. So this implies that F box F is less than equal to F. Okay. On the other hand, so F box F is, well, it's what? It's B cross B And then you have, oh my gosh, so this push-out product source thing, which is, well, it's A cross B union over maybe A cross A, is that right? B cross A, something like this. I think that looks right. That would be F box F. Okay. And then I have the diagonal, but modalities are closed under pulling back by any map. This is essentially their definition. I think Edward showed us this before. Modalities are closed under pullback. If I pull this back, this map right here, let's call it X, I forget what it's called. But this map has a name, it's the join of F of itself. If I pull back along the diagonal, I get the join of F of itself. So that means that the join is less than F. But this is one characterization of what happens of monos, is that they're exactly the idempotents for the join. So I have this. So I now have, well, let me see. So I have F is less than or equal to F box X. So then, the other way around. So F and F box X, F, when F is a mono, generate identical modalities. There's no difference between the two. So that just says that the higher powers are constant. They're always the same modality. I don't add any more maps by taking powers of a monomorphism. Okay, so, and in fact, right, every modality, if I have P, sorry?
But F itself is still a non-trivial.
Right, that's what I was just about to say, is that every modality generates what I would call a topological modality, which I'll just write like this, which is I take my family P and I truncate, I -1 proposition and truncate all of its fibers. This is what you might call the topological part of my localization. And that's what goes right here. Okay, this is the topological part of this localization. Okay, so this is why this tower that we've constructed lives entirely within what you would call the co-topological part. Because if I localize, if I first pass to the topos where all of the things become non-empty, in that topos, my family sort of, I can look at the image of my family, it's now surjective. So I'm in this other bizarre case where I have a Lex modality generated by a surjective map. And this is what people call a co-topological localization. Okay, yeah?
So thinking of this as a formal neighborhood, is the infinity connected, is that the limit?
This is unknown. Yeah. This would be a fantastic, it would be a beautiful fact if this was true. And I think we've been trying to prove it for a while, and it's unknown. So go and prove it. You can report back to it.
So what would be the fact?
That the inverse limit of this tower is, more generally, you would like to know, so you have any localization, and you'd like to take the inverse limit, its sort of completion tower. Does that always give you the, it's not going to converge to E in general, but does it converge to the topological part of your localization? That would be nice, but we don't know. Yeah, I'm going to know that.
You want a state conjecture?
No, because I really don't know which. I really think it could go either way. It really could be one or the other. It would be beautiful if it works, but and there's evidence that it might, but there's also evidence that it might not from topology. So I don't know. I just don't know. Okay, I have 10 minutes. Is that right?
That's right.
Okay. So, yeah, I hope that I sort of simplified the picture from yesterday. So, or from Wednesday. The picture from the other day was you needed these complicated colimit cubes. And you need to take their pushouts and their pullbacks. We need not define in type theory. We need functor categories. We need all this stuff. Here, sort of what we're saying is the Goodwillie tower is just completely generic inside of type theory. It exists for any Lex modality. Okay, so let's see if we can derive, can we say anything about it? Well, here's one curious thing you can say about it. So I'm going to still use this picture because I don't know how to write this picture in type theories. That I have E and I have my localization. Maybe I should call it E mod P. That's probably a better notation. I don't know why I switched.
Yeah, that's the reason we were using double slashes. It's not a slice of the
No, that's right. I want to distinguish it from the slice. I'm thinking of this double thing as a quotient of the topos, localizing the maps in this family. And that makes sense if you think of the topos as a space and the logical version as being a sort of algebraic object. This is kind of.
Can we always construct that localization in type theory by Egbert topology, or?
That's yes. So it's exactly the same thing. It'll be the nullification, and if P is closed under diagonals, it's just that. And yeah, it's just that in type theory. Exactly. So it's kind of a nice simple picture. Okay, so we have this tower, E sort of mod N, and pictures. And what I want to sort of analyze, this goes off to something. There's the inverse limit, and there's the topological piece, and if they coincide, maybe they don't. So what I want to ask about, what I want to think about, is what are the objects living here? Well, I want to think intuitively, I want to think about the fiber of this map. I want to imagine, so this thing has a terminal object. If I think of these as categories, there's an inverse image, and I'll write out in type theory what that is. So I want to imagine objects that are in this fiber. Let me call it H. So, okay. So what does this mean? This means thinking about objects. A is maybe not a good word, but well, A is good. Okay. I want to think about objects that are P box n plus 1 global. Remember, I have P, my original Lex modality, and now I can think about the local types for its nth power. And I can also think about the types which are P and connected. Okay. So if I have these two conditions, that's what I'm thinking of as the sort of fiber of this, yeah, in Goodwillie theory, people call these the layers somehow of this tower. And the main result about this, which I don't know if I'll have time to prove, but let me just state it. So let me suppose, let's suppose that a square. And I want to assume that A, B, C, and D satisfy this condition. Okay, so I have a square of functors, if you like, in this sort of fiber between these two layers of this tower. And so the claim is that the following are equivalent. One is that the square is a push-out in this topos. So let me in the local topos. Okay. So here you have to be careful here because I mean that it's a push-out here and not here. So that this is equivalent to. Let me write. There's a universal map that goes right here from the push out to right here. So that's, and let me write that map H comma K. So the sort of the co-gap map between the push out right here. So being a push out square in this local topos is the same thing as saying that this map is P blocks n plus 1 connected. Okay, that's just the same thing. Connected. That's right. Okay. So exactly. So I have an object in these fibers. I want to look at push-out squares in this local topos right here. And so two of the squares. So okay. So you may, yeah. So people who do infinity category theory, they recognize this. This is almost saying that this is a stable infinity category always. The only difference is that in general, without picking base points, it won't have an initial or terminal object. It won't have a zero object unless I pick sections. So yeah.
Is it topos? Is it fiber?
No, it's not a topos.
So you took a fiber.
I took a fiber in categories. It's not. I'm
Right.
just looking at the because this condition. So this the collection of all types that are Pn local is always a topos when it's left exact. But if I add this condition, this is not all types anymore. It's some subfield.
Do you know anything about the topos theory?
No.
If toposes are rings, then the
probably,
type coil is an ideal and not a ring again. So.
Yeah, exactly. Exactly. Yeah. Okay.
Let's save the discussion.
So how do you see this? So this is a proof. This is well, not proof. The proof is what I'm going to is essentially the generalized Blakers-Massey theorem. So I'm going to apply the Blakers-Massey theorem to this square, and there are sort of two. So what does the generalized Blakers-Massey theorem say? So I can give a sort of cute formalization, a description of what it says. Maybe I transposed from the last word. Sorry about that. So the generalized Blakers-Massey theorem it says not something. The original one says something about connected maps and how they interact with push-out squares. The generalized version can just be given directly as an estimate of this map right here, what we call the gap map. So this map F already is FG, which is the map from A to B crossover to C. And I'm going to estimate this map with what I'll call it with one of these inequalities. Okay? So the Blakers-Massey theorem can be asserted as saying that for any push-out square, this map is less than or equal to this map. Okay. So so this is the content of our so it's a sort of abstract version characterizing the fibers of this map in terms of how we'll find the fibers of this map. And you see right away that if F and G are, say, N and M connected, then this will be N minus 1 and M minus 1 connected. And then the box product is the join, so you add them together, you add 2. And so you'll see that this is N plus M. Okay, so it's a sort of immediate consequence of just playing with okay. And there's a dual estimate, which is that if the square is a pullback, then you have, this one is quite a bit easier, that this other map is less than or equal to just this without the diagonals. This is considerably easier. This is just this is essentially just universality of colimits. So this is not a complicated fact. Okay. So those are the two. So if the square is a push out, I think I'm out of time. If the square is a pullback, we have this, and I need to give a slight variation. So the variation is oh, this is funny. I think I flipped now twice. Am I back where I started? So this is a Z2. So I can rephrase this a little bit by saying, so here I had to assume for the first line that this square was a push out, but let me not assume that. Let me just say completely generally that this map for any square is always less than this. And then I need to do one more thing. I need to just force it to be a push out. And it turns out when you do that, you end up picking up an extra diagonal. So it's the diagonal of H. Okay, so this is complete. This is true without any assumption. This is true for any square, this estimate. Okay. So, okay, we're done. I mean, so now we just need to analyze these two things. So, so I said the square is a push out in this local thing, amounted to the assertion that this map was connected. Right? So let's just check. So let's check 2 implies 1. If the square is a pullback, then this map is by this over here, it's controlled by f box G. But this is a Lex modality, and these A and C and A and B are n-connected types. Well, n in this sense, p n connected types. So because it's Lex, any map between them is n-connected. So if I box them together, I'll be far beyond n+1 actually. So I'm not giving you the optimal version of this theorem, but in any case, that will show this will actually be p 2n box connected. So it's certainly p n box connected. Okay, so I'm just, yeah, there's this slight, you can make it stronger, but anyway. So that's 2 implies 1. It's just a sort of direct application of this. In the reverse, I have this variation right here. And the point is, by what I said before, every map here is a p box n connected map. Okay? And this uses the fact that we're dealing with Lex modalities. And it's also Lex because so all these things are connected maps, but it's a Lex modality. So that means all of these things are also Lex modalities are closed under taking diagonals. So that means that I can, well, I mean, everything in my picture right here lives in the P2N connected maps. So this box here will also live in the P2N connected maps. But then it's a P2N connected map between P(n+1) local objects, so it's an equivalence. Okay, so sorry I ran out of time, but this is if you work out the this is it's an application.
So the other day you told us that how P1 recovered loops infinity, sigma infinity, that's the identity.
Right.
Do you see that?
You see that if you calculate in this specific example.
Yeah.
In the general case, sort of anonymously. So this is what I wanted to say. Okay, so well, let me just make one comment about that. Okay, so let's suppose. Let's just take this for n equals 1. I mean, this will work in general. So if I'm in this situation here, then one particular example of this is this pushed out square, because this is always Pn local for any n and Pn connected for any n. So I'll have this situation right here. But that says actually that this map is just that in that particular case, this map is an equivalence. So not only do we have, so you see we sort of internally inverted the suspension function. We have these types with the property that if I take loops on their suspension, I get an isomorphism. Okay. So this is the sense in which by performing this operation, we have an internal version of stable homotopy theory. We have types which think they are stable homotopy types. And so so this is true always in the tower, but higher in the tower above 1, there's stable homotopy types with extra structure. So I didn't describe that structure today.
But you said that the universal one is in this one there.
Yes.
The first one is P1.
Yes.
There you just got spaces back.
That's P0. Oh, sorry, I had it off by 1.
Okay.
So nullification of x to the n plus 1 is the n.
Okay, got it.
Sorry. Yeah. And and if you nullify with respect to x squared, x itself, yes. In the model, this is exactly this respect.
Will there be a formalization soon of the Goodwillie theory?
Yeah.
It looks like you're really close. It looks like you're really close to being able to do it.
Oh, absolutely. Yeah, it's absolutely doable. Yeah, there's The Blankers-Massey theorem, the generalized one, is basically done in AGDA modulo, a stupid thing about equivalences that I haven't fixed, but it's essentially formalized. Mike already formalized the things about Lex modality and Conc.
Okay.
So those theorems are essentially done in Conc, so we just need to put everything together, but the whole story is already there. There's no obstructions to do.
We expect to see that very soon.
Okay.